In this clip, we'll get a conceptual understanding of two kinds of classifiers: linear discriminant analysis or LDA and quadratic discriminant analysis or QDA. Now, before we get to LDA and QDA, we'll take a little detour to understand the importance of projecting your data. Now, here is a pop quiz for you. Do we really need two dimensions to represent this data that you see here on screen? The answer to this question, as in the case of most of the questions in the real world, is it depends. Now, if you choose our axes or dimensions poorly, then we do indeed need two dimensions to represent this data. On the other hand, if we choose our axes or dimensions that we use to represent this data well, then one dimension will be sufficient, as in the case of the example that you see here on screen. And this, in a nutshell, is the intuition behind an important dimensionality reduction technique called principal components analysis. Given a set of data points, your objective is to find the best directions to represent this data. What are these best directions? Let's say you start off by projecting all of this data onto a line in some direction. Let's say you pick this direction at random. Now, the direction that you've chosen can be considered to be a good one if the distances between your projected points are as high as possible. Greater the distances between these projections, better the direction that you've chosen. On the other hand, a projection where the distances between your points are minimized on the projection line is a bad one. Information is lost. A good projection is one which preserves the distances between your points. Now that we've understood the difference between a good projection and a bad projection, let's go back to the data that we were working with. We've projected these data points along a line where we've tried to maximize the distances between points on the projected line. Another way to state this is that this projection preserves as much of the underlying variance in the data as possible. Now, this direction along which this variance is maximized is said to be the first principal component of the underlying data. Once we have the first principal component, we can move on to finding the second principal component. This is the next best direction, which should always be at right angles to the first principal component. Why right angles? Well, this is because directions at right angles help express the most variation with the smallest number of directions. It's pretty clear here that the variation in the underlying data captured using the second principal component is much smaller than the first principal component. And this is by design in principal components analysis. In general, there are as many principal components in your data as there are dimensions in the original data. So if your original data could be expressed using two dimensions, it will have two principal components. And these principal components are directions which capture the maximum variance in your data. So instead of expressing your data using the original coordinate axis, imagine that you've re-expressed all of your data points, reoriented your data along these new axes, which are your principal components. This is the principle behind principal components analysis, which is a dimensionality reduction technique. Now, this is important to understand in order to understand how linear discriminant analysis works. LDA is very similar to PCA. It uses the same underlying idea of projecting points onto different axes. The difference between LDA and PCA lies in how these axes are chosen. LDA chooses axes to minimize the distance between points in different categories. Now, if this is not really clear, let's use a visualization to understand what's going on. Here we have some points represented using a 2D coordinate plane. Now, these points belong to different categories represented by the green, blue, and red colors. Let's say you wanted to project these points along a line in such a way that the different categories are preserved. Now, if you were to choose a line that you see here on screen, that is the worst one-dimensional subspace that you could use for projection. So you have your original data points and you project it on this line. You can see that the differences between the categories are basically lost. On the other hand, you might have chosen a different one-directional line to project your data points. So here is a 1D subspace, which is the best possible 1D subspace to preserve the differences in your categories. Observe that this projection preserves the categories that exist in your data, and this is exactly what linear discriminant analysis does. LDA will try and find those axes to project your data points, which will preserve the different categories that exist in your data. Now, quadratic discriminant analysis, or QDA, is a variant of linear discriminant analysis that is better suited to cases where X variables corresponding to different Y labels have different covariances. Now, this definition is rather a mouthful. So let me first define what covariances mean. We talk about the covariances between X variables. Covariance measures the relationship between two variables, specifically whether greater values of one variable correspond to greater values in the other. That's when the two variables are said to have positive covariance. With this understanding of covariances, let's go back to our definition for QDA. Now, let's say we have different Y labels or different categories, such as blue and green in our data. Now, for all of the data where the category is blue, if the covariances of the X variables are very different as compared with the covariances of the X variables where the category is equal to red, that's when you'll use QDA as opposed to LDA. Let's imagine this with a visualization. You have two categories of data here, red and blue, and LDA works fine when the X variable share uniform covariances and are completely independent of the Y category, red or blue. But you'll find that linear discriminant analysis fails when the covariances of the X variables are a function of the value of Y. The covariances of the X variables are different when the category is blue, and they are different when the category is red. Very simplistically here, you can see that the way the red dots are spread out here in this 2D visualization is very different from the way the blue dots are scattered. This is where you would not choose the LDA. Instead, you would use quadratic discriminant analysis to separate and classify your data points. So if your X variables have different covariances based on Y category, QDA is preferable to LDA.